Hi, Ethan.
Hey.
Hey, guys. Get a drink of water here for a second. Did we talk about proving stuff last night? Somehow I have this recollection I mentioned the Pythagorean theorem, but maybe it was my other section. Did that get discussed at some point? Abe, do you remember? Did we talk about the Pythagorean theorem for some reason?
No, we didn't talk about Pythagorean theorem.
Because somehow maybe it was the other section, but we were wondering about the proof of the binomial theorem, and it just did I somehow get into it's something about how tricky would it be to prove the Pythagorean theorem? I don't know. I thought getting old, maybe senior moment, maybe that was the late hour. Nobody has any recollection of that, huh? Okay. It's funny because I actually had looked up a proof of it, and I think there's something like 50 proofs of it, and one of the proofs of the Pythagorean theorem was by a U.S. president.
Really?
Yeah, President Harrison or something. I don't know. That's probably what do you call that? The ancient era of U.S. presidents. But when you think about it, how would you? I mean, I'm just curious. Are you guys sophisticated enough to just do it within a products or something, or do you want to just take a quick look, or no, we're wasting time?
Take a look.
Well, that's just you. Aim, or you? Maybe not. Or
it's by Garfield.
Garfield.
The proof is by Garfield.
Very good. And how long ago did he do this?
How long ago did I know this?
How long did he do it?
Oh, I have no idea.
That's good. Presidents have changed since then, But oh well, I'll forget it. We won't do it because I feel it's wasting time. That we could do a statistic, probability. I don't know how it came up in the later hour, but it just came up. Okay, so let's. What did we not do last time that was important? Okay, so as far as these chapter 4 random variables, there's one that we didn't do. That's used a lot in it's called the hypergeometric. Okay, so hypergeometric random variables. So what is the setting for this? Okay, so you have an urn, and it's got m white balls and n minus m black balls. So let's see. So therefore, how many does it have? That says n total. All right. So let's look at the sample size. So suppose we take a sample size is, let's say, n. Okay, so then we would like to know, okay, so the random variable will count, say, the number of white balls, okay? In the sample. So this shouldn't be too bad. So what are we trying to prove here? We want to know what the probability mass function is for x. So let's say, what is the probability that in the sample? Now, of course, you have to, we're assuming that I is less than or equal to n. But getting I white balls in your sample, what is the what is that probability? So how do we do this? Well, we've done this similar things, right? How many ways could we create a sample of size n? Well, you have a total of n balls here, and little n, a sample size little n. That's how many total samples are. And so how many samples would have the property that there's I white balls? Okay, so you have m total white balls, so you can, how many ways can we choose I from that? And then the only complicated thing is, what about the rest of it? Well, you're choosing I white balls, and that means there's n minus I balls left to choose, right? Because the sample size is n, small n. Okay, so it's n, so we've already chosen I. I lost my train of thought here, so I'm going to choose from these. How many balls are left here? So of the other, the black. So you have your sample is size n, but I'm choosing. I'm going to be careful here. How many am I choosing? So there's n minus m black balls. So of the n minus m black balls, I want to choose how many? N minus I. Good. Pass the test, at least for there. So this is the distribution of the probability mass function for the hypergeometric. So notice that these balls are being removed without replacement, right? So you can. There's something that's worth. It's a thought thing we should think about. If the sample is really small compared to this gigantic urn with all sorts of balls, there shouldn't be much difference between replacing and not replacing, right? It should be about the same. So in that case, that you can probably think of this as a binomial. In a limiting sense, it starts looking like a binomial distribution, where whatever what would be the success probability here? You have m white balls, so it would be of getting a white ball would be m over capital N. So it's in terms of computing the expectation, the variance. You can sort of, this is, I guess, a way to remember it. You just pretend like it was the binomial. We already know. Let's see, what do we know the binomial mean and variance? I don't know that I did the variance, but anyway, what is the binomial variance anyhow? What's the mean of the binomial? Let's just review real quick. What's the mean? And what is the variance?
I think the variance was NP 1 minus P.
1 minus P. I don't know that I did that, but anyhow, this looks very complicated here, but what I'm trying to say is that if capital N was really huge relative to that sample, it would be equivalent, sort of equivalent to a binomial situation. The success probability is not going to change that much. All right. Okay. So let's try to do a problem here. Let's try to do an example. And I'm sorry, I'm a little bit. I had a very tough departmental meeting yesterday, so it's the effects of it are lingering. Okay. So at some point in this lecture, I'll do an example of this binomial, this hypergeometric. I'm going to see where it is. Hold on a second. Well, let's just try this problem. I don't remember if it is because I prepared these notes a couple of days earlier. But let's see. The book does have some classic example of this. There is a classic example of it. Sorry, I'm just stretching my mind a little bit to remember it. But it's something that biologists do to estimate the population size. Oh, what happened there? Did I make a mistake?
No, I'm just writing it in rewriting it so that we can tell which ones are M's and N's.
Oh, okay. It's N is this, and then M is this. The sample size was N, as in Nancy. There is this classic a classic example where biologists, have you ever seen such an example? They're trying to estimate the size of a population of fish. There may be multiple species of fish, but in a lake. And does anybody know what the technique is? I'm going down a rough road here because I haven't thought about this for a while. But it's just I'm just giving the general problem. So this is a lake, and there's a species of fish, and you're trying to estimate the population. How is this done? Do you remember I remember doing this in high school biology. But what do biologists do? What do they do? I mean, they could get a fish finder and do something like that. But I mean, really, what is the classic way to do this? Assume that you have to assume that the fish are sort of uniformly, distributed or something like that. They're all bunched up. So how do they do this? Does anybody know? Okay, I guess we don't have biology people here. But what they do is they take a sample. They just withdraw a sample from here, and they tag all this. So you take a sample, say a size n, as before, and you tag these fish. And then you release them. Okay, so you release them back into the water, and what do you do now? Okay, so what this doesn't make any sense. They're going to release them, and they're going to. What's the technique here? Then they're going to take another sample and find out how many in that new sample they're tagged. And you see, if there's two species of fish, you something called the maximum likelihood estimator. You try to figure out what the population would be to maximize the probability that you got that particular your sample was that your sample occurred. For a different population, there's a different probability that the sample will have a different proportion of the fish that are tagged. You get the idea? So this is a standard technique, and I guess it involves this hypergeometric. You have fish that are tagged, and you have fish that aren't tagged. So there's two, it's like the white balls and the black balls and stuff like that. And you don't know the population, but you do know what would be most likely. That's statistics kind of thinking, right? What's most likely given the result that you got. So that's the classic use of the hypergeometric, and you can see it, read about it in Ross. He gives a long thing, and it's very unfortunate because all this analysis that he does can be, if you just take a ratio, a simple ratio, proportional, and you get the right answer. I don't know, it's just crazy, but of course this is not the end all of the use of this random variable. Okay, so that's enough of that. Okay, let me attempt a more tricky problem here. This is a long sequence of binomial distribution problems. I think it is that, but if it isn't, then you can kill me. Okay, so let's look at example 8I. Okay, so and stop me if I've done it before, but I don't think I did it. So you have a product that's coming in, items are coming in lots, and the lots are size 10. And there's an inspector who his job is to do something quick and dirty with the lot to decide whether to accept that or not. It's sort of an honor among thieves situation. If you get that. So he's gonna expect 3 items only. So inspect 3 items only, and there's 2 outcomes here. But he's either going to accept it or not, or reject it. But he accepts only if all three are good. So he's taking a sample size 3, and he's only going to accept that lot if all three are good. Okay, that's not a very interesting problem. But it turns out that there's 2 species of lots here, okay? So there's 2 types of lots. What are they? The first type is 30% have 4 defects and 70% have only 1. I hope my handwriting is clear enough to see that. So the $64 question is, what proportion of the lots does the inspector reject? And I want to be, because what proportion are rejected? Okay. I guess, what would you do? I mean, so what rule of calculation and probabilities do we want to use here? So this is okay. I don't want to give any hints. What should I do? Well, how about an event? How about E as the event? Event inspector rejects. So what's the rule here? So the rule of what? So what's our plan of attack for something like this? I want to calculate P of E. So what is the general? Anybody can speak. So maybe it's too easy for you guys. You guys have grown up beyond my ability to teach you. But what is this rule that we want to use here? Or if this is from the first test or something.
Trying to remember it. I think we're conditioning on whether it's a good lot or a bad lot.
Exactly. But the key is, it's called the rule of total probability, the law of total probability. We have to make sure that our events are exhaustive. That's like the only tricky thing here. And it is exactly as Ames says, this is conditioning. So what would be those other, so A is you're in the 30% category, cat, and B is the 70% category. But it's either one or the other. That's what makes this problem doable. So let's see if we can finish it. There's no guarantee. So the probability. So this would be the probability of E given A times the probability of A plus the probability of E given B. I know I'm in the way. I'm sorry. Okay. Well. This is probably going to end up being a binomial thing. I'm not sure. What's the probability that we reject, given that we have in the 30% category? Well, you're in the 30% category. You have how many bad ones? You have 4 defects, right? So there's 4 defective ones. So the probability you reject is you hit one of those, right? So let's do a scratch thing here. So how do we, what's the probability that we hit? So our success probability is what? Success probability is what? I can't write an angle, sorry.
So like success means that we're going to, like the inspector is going to reject it. So he would need to find 1, 2, or 3.
Well, no, there's 4 defects here, right?
Well, isn't he going to try? He's going to inspect 3 items, right?
Yes. Right. Okay. He's going to do this.
Like when I see with the 4 defects, well, I don't know. Man, I got to think about it.
Yeah, hold on. But it's not in a rush here, especially today. Okay, so let's try to figure out what the situation is. We want to know what's the probability that we hit. Yeah, right. Well, it could be. You're right. It could be 1, 2, or 3 defects, right? So this needs some kind of investigation.
Well, since we're doing this without replacement, it's not binomial. Like I think this is where the hypergeometric comes in.
It seems like it. It seems like it. So it seems like it. So what is that situation? So we're in this case here, and we want to know the probability that we get. Well, that's hypergeometric. I mean, it's still 3. It can end up with 3 cases. So maybe we should go 1 minus to try to find the probability. Let's just do this slowly. So the probability of me given A, what is the probability that I don't get it? So then I get a defect. Right, wouldn't that be 1 minus the probability of avoiding the defect? All right. Okay, so the probability of getting no defect, now I have to take a sample of size what? And now let's do the hypergeometric. So how does it work? We're taking a sample of size 3. Let me write down just to make it easy. Let's try to fill in these numbers here. So we want to know the probability that I get 3 good ones, right? 3 good ones here. So my sample size is 3. So n is 3. How many do I have altogether? 10, right? So of course I'm in a position here where I can't rewrite this. Darn, I hate this being squeezed by this board here. And I think we know the situation. I can probably go this way. Okay. I'm trying to evaluate this right now. Not this, but this. So m, let's say that m was, what are we shooting for here? We want to get no defect. So how many ones have no defect here? 6, right? And how many are we selecting here? They're selecting 3, right? Times what? How many total are in here? 10 minus 6 of the other ones, and 3 minus 3, so that doesn't do anything. And then how many total again? We have 10, and the sample size was 3. Okay, so what I'm getting is this, whatever this is, for the getting a sample of no defect. So it's sort of a hypergeometric thing. Okay, but what is this? 6 choose 3. I probably should know what that is. What is that? 4 over what? Is it 20? So it's 20 over whatever 10 choose 3 is. 8. I don't know. So 2 goes into 4. Is it 120? I don't. I need a calculator.
6. So hold on. I mean, I just have a calculator. 6 choose 3 is 20.
Why did I get? Yeah, I was doing 10 choose 3. I'm doing the denominator.
10 choose 3 is 120, yeah.
120. So 20 over 120, it looks like 1 over 6. If I did this right. So okay, so let's put in some of these numbers provisionally right here. So if it's 1 over 6, what is the probability that I get a defect in this case? 1 minus 1 over 6, that's 5/6. So that becomes 5 over 6, provided I did this calculation right. Then what is the probability of being in group A? 30%, right? Okay, so Should I double check this to make sure this is right? So maybe I should. Maybe that's the thing. So how many defective ones? I'm looking at the probably no defect. So the ones that were not defective, there were 6 that were of that type that were not defective. So I'm taking all 3 from that and choose this total of 10 and I'm taking a sample of size 3. So, okay, this looks correct to me. So anyhow, so this is what I'm getting for this. But what do I get for this? Well, probably going into B is 0.7. So how do we calculate the other part? I'm not checking my chat, I'm sorry. It looks... So let's calculate the other thing. So what do I need to do for this? I want to calculate the probability of no defect. And that would be what? That means let's fill this in here. So again, I'm taking a sample of size 3, the lot's the same size, so it looks like it's 10 choose 3 in the denominator. But the M, if we're in this 70% category, what was the story? 70% of this type, but how many are defective? I've erased it over here, but I think they only have 1 defect. Okay, I think that was the story of this problem. Okay, so there's only 1 defect. So not getting a defect. So that size that would be 9 choose. There's 9 that don't have a defect, but I need to choose 3 from that. And the other thing shouldn't be, the 3 and the 3 cancel out. So this is what I get for this. So and now I need to do is calculate this. 9 choose 3 or 10 choose 3. What is that?
84 over 120. And then simplify that.
What is it? 4.
That's 0.7.
0.7. Okay, so thank you. So if that's 0.7, then this must be what? If that's 0.7, this must be 0.3. I hope it's right. I should have done this at home. At least I should have done it more carefully. What answer am I getting? I don't know where to go because I may have to redo this, but let's see. Numerically, what answer do I get here? So 5 over 6. This is the probability of rejection. So 5 over 6 times 3 over 10 plus 0.21, whatever it is. 0.21, 15 over 60, so it's 15 over 60 plus 0.21, what is that? So 15 over 60, that's 1/4, 0.25, 0.46. Anyhow, I'm getting 0.46 rejection. I don't know. Is my answer going to be rejected by the book? I don't recall this answer. So does he? I don't know that I.
Well, and I put it in my calculator. I got 0.26.
Oh, really? Well,
yeah, for the whole thing, right?
Well, the whole thing. Okay, so 5 over 6 times.
Oh goodness! Hold on, 5 over 6. Hold on, that changes it. Let's change that to 5 here. Yeah, I got 0.46 as well. Sorry.
Okay, so I think the book did this problem completely differently. So, but my recollection is that perhaps this is the right answer. I hope it is. I don't want to look. I'm nervous. But anyhow, I think they did it differently. They set it up differently. But I thought to do it, I think they did it for the probability for acceptance, and they 1 minus that to get this. But let me check it. If it's wrong, I need to fix it, but I'm not going to fix it right now. What was this again? This was 8.9. Okay, they're saying that 0.46 were rejected. So that's what we got here, okay? But again, they did it a different way. So thank God that I was able to survive that. Okay, so again, so what's this using? It's using the rule of total probability, and as Ames said, it's supposed to be using the hypergeometric, but not in a very, not in a very interesting way, because one of these numerator terms is just one. So it's like a weak example of it. All right, let's look at something more interesting. If I can find it. Okay, so this is probably about my last problem I'm going to do out of the textbook. But I found
Can I
this.
ask a question, Professor?
Yes.
For the second term, you have the probability of E given B. Can you explain how you got 0.3 there? Because I thought it was 0.7.
Okay, so the B case would be the 70%, right? So let's look this over. So that's my recollection. The A case was 4 defects. The B case was 1 defect. So let's check that out. Let's draw a picture for that. So 70% of the time we're in a situation where we have only 1 defect. So I guess I could go over here. Let's check it out. So I'd like to know the probability of, given that we're in that situation of having only 1 defect, what's the chance that the sample of size 3 doesn't include any? So any defects. So I need, I would need 1. Okay, so we want the probability of getting a defect. And that'd be 1 minus the probability of no defect. So this, what I'm focusing on or trying to do is to focus on that, if I can spell right, that probability right there. So getting no defect is what? That means the defectives, you only have 1. And I'm trying to get the probability of null. So let's see. So the number of, how to do this? I know I'm getting lost here. So n was what? N was the number of good ones here. So that means I have 9 good ones, and and we're taking a sample of size 3, right? And the other term is 0. So I'm just going into this. So there's 9 good ones. I'm taking a sample of size 3, but you see this. You're saying we're going to take 3 from the good, but you see it's a sample of size 3 and the 3 from the good, so that's 3 minus 3 is 0, so that goes away. Then n here, the total is 10. And our sample again is 3. So this is all possible samples of size 3, and these are the number of samples that don't have any defect. So I don't know. I've forgotten now what these numbers were because I erased it. But sorry. But what did this? Does that make any? Am I making any sense? I'm not sure. What I'm doing is just fitting it into this formula and realizing that this n is 3 sample size, and there's okay. I was the number we were taking of from the ones without defect. So 3 minus 3, that's 0. So this is nothing with this. So it's just these 2 right here. I'm sorry, I've forgotten already what these numbers were. What was it? 10 choose 3 was 120. What was the bottom one? What was the bottom one?
Well, it ends up being 0.7.
Oh,
The answer. Yeah, that's why I was confused, but it makes sense. 1 minus 0.7 is 0.3.
Right,
so
no,
I think, okay.
No, hold on. I think the answer is supposed to be 0.3 here. So this is 0.7, but 1 minus 0.7 should be 0.3. It should be 0.3. right? Because that's what we put in right here. This 0.7 went with 70% of the lots have that property of only one defect. Okay, so I'm just confused now. I forget, what was this guy, 120? What was this guy, 9 choose 3?
84.
Thank you. So what did we get out of this? 4 went in there. So, so what? 4, I don't know what this was. 4 goes in there 30 times, 4 goes in there 3, 7 over 10. So this is 0.7. So this guy's 0.7, but 1 minus 0.7 is 0.3, and that's this 0.3 right here. I guess the confusion is that the numbers look similar, but the 0.7 came out of the proportion of the lots that were of that type that only had one baddie in them. Yeah, I can understand the confusion. It's the same numbers. Same number it occurs in 2 different contexts. Does that help at all? Or,
Yeah, I guess I was just confused what E and A were. I can't really. What is E again?
E is the event the inspector rejects the lot.
Okay.
So he rejects it. So we're trying to express this somehow in terms of the 2 different types of lots that were there. So 30% of the lots had 4 defects, and 7% of the lots had 1 defect. So either he's going to pull the A-type lot or a B-type lot. So what we did is, because those are exhaustive, what we did is we used the law of total probability here. And we figured out these individual things and we multiplied it out, and supposedly we got the right answer. This is the probability. I realize this is different than how the book does it. But I'm looking at the probability that he rejects. And he'll reject a lot if he finds even just one bad item. So, it's easier to calculate that is to calculate, well, take 1 minus the probability that you don't get any bad items. That's the no defect. So there's a couple things going on here, right? The complement, the law of total probability, and this kind of weak use of the hypergeometric distribution. But if you have any question, ask me now. I don't want to. I think this was just icky looking. It wasn't like deep or anything. Are you good with this? I mean,
yeah, you clarified my
okay,
question.
you're good.
Thank
You're okay.
Yeah.
You're okay. Okay, just want to make sure. For the next test, I probably, if I put it hypergeometric, I'll definitely have both sides going, full bore. I won't have it just what should I say, a sort of kind of a collapsed version of the formula. Okay, let me just check the chat and make sure there's no other question. Okay, so the next problem is, it's rather interesting. And I taught this course before, and something happened. There was a student that was doing problems from the book sort of randomly because she wanted to go into statistics, and she ended up in a PhD program at Duke University in statistics. And apparently Duke is a big time place for statistics. Anyhow, she got this problem. She found it in the book, and she asked me a question which I didn't know how to answer. Hopefully I can answer it now. This is the classic. Exercise 4.50. $4.50. Okay, so this is a situation where we're tossing a coin, and it is not necessarily a fair coin, okay? We're tossing a coin 10 times. So toss, this is important. We're tossing 10 times. And it's not necessarily fair. The probability of heads here is P. So obviously the probability of getting a tail is 1 minus P. What Twilight Zone assumption are we making here? What happened in that Twilight Zone episode when a coin rolled around? You know what I mean? They dropped a coin and rolled around. What happened? I'm testing you guys if you know the Twilight Zone. What happened?
I don't know that episode.
Well, it landed on the edge. And all sorts of weird stuff happened after that. But so
that's funny.
in that case, you see, you wouldn't have P and 1 minus P, right? There would be a third option where it just stays on edge, like just hanging out without flipping either way. So we always assume it's either heads or tails. Okay, so this is the thing you have to calculate. You need to calculate the probability of getting this front end. So heads, okay, I'm doing something different in the book, okay? I changed it up just a little bit, what the sequence was, but you can do it, Given that 6 heads occur. So this, let me emphasize, that's the front end. What the probability is you flip the coin 10 times. Given that 6 heads occur, what's the probability that you get this front end? Now you might say, I know what I got. It's like you're looking at it. I know what I got in the first 3 tosses. This is different. Let's say the experiment has happened. You did not watch it happen. All you know is that the front end was heads, tails, heads, and that you had. You knew in advance that somebody told you, by the way, there were only six heads total. So just, this is a crazy thing, you guys. So what do you think the question was that this student asked me? There's something about this problem that appears on the outside to be rather weird. How would we, let's just start thinking about calculating this, okay? Also, let me emphasize here, the probability of heads is P, and the probability of tails is 1 minus P, okay? It's not a half and a half, say. Okay, so when we're doing this conditional probability, let's go back to the definition here. This is sort of a trick question I'm gonna ask you, but how would we do this? What's the probability that you get 6 heads total? This is just a review. So that you have how many reps and they're all this independent and the same success probability of P. This is a binomial distribution problem. So let's figure it out. How do you do that? What do we need to put down there? You had 10 tosses. What's the probability of getting 6 heads? How do you calculate that?
6 choose 10.
And the other way around.
Oh, excuse me. Yeah, 10 choose 6 times just P to the 6th.
Yes.
And 1 minus P to the 4th.
Yes. Very good. Okay, now comes the hard one. Knowing that you had 6 heads, this is tricky here. Now I got to figure out. 6 heads. What's the problem? 6 heads occurs, and you get this result. Well, 2 different things happened here, right? You have this, and you have this. Well, excuse me. That's. Forgive me. I just said the wrong thing. So erase that tape. What did happen here? You started out with this, right? But you also have 6 total heads. So we start out with this, and that means that for the next, how many more do we have left? 7 tosses? What has to happen here? How many heads did I use up? 2, right? So let's count the number of cases where I've got this front end, and I also have a total of 6 heads. So that means I've got to have 4 heads occurring over here. So how would I calculate this portion right here? And again, we have this sort of event happening, and then we have this event happening. Those are independent, except for this story about the number of heads. So we know we have to figure out how many ways can we generate sequences of leaf 7 that have 2 heads. So how do we do that? What would it be? Well, you have 7 trials, right? So 7 trials, and we want to know the 2 heads, and then what do we have here? We have p squared times 1 minus p to the 5th. But how am I going to say that this is what happened over here is independent of this, except for the fact that you're constrained to have 2 heads. Well, this is the probability that in this event, okay, that you're getting to. So what do we think? Now, maybe I'm making a logical error here, but let's put in what this is. If it's probably this times the probability of this event over here, I'm going to be very careful here, because I don't know that I have an answer.
So hold on, I'm not actually 100% following here, because we have 7 more tosses. I agree, but don't we know that there's going to be a total of 6 heads?
Oh, did I say 6? I'm sorry. I can't even follow my
So
own.
we would need 4 more.
6. So that should be 4. Right. Sorry. Right. And there's 4 of these. So that means there's total 7. There must be that many tails here. Okay, so my difficulty right now is I'm having some trouble with independence. But I'm looking for the probability of this happening and this happening here. And I want to multiply these things. Maybe I'm making an error.
Okay, well, the formula is for this conditional is the probability of A and B.
Right.
Like we want both of them to happen. So right
Yeah.
now, all that we're doing is describing the situations where both of them happen.
Yes, but here's the problem. If you take the probability of A and B, it is not always probability of A times probability of B, only if they're independent, right? And I'm thinking, I know this is independent, but I have to give a reason for it, and I'm in trouble. You see, because it's not. Sorry, guys, I'm just drawing a blank. I don't know why these. I mean, definitely the sequence. Whatever happens in the sequence here, but we want to. Okay, this describes a lot of different sequences here, but they all have that property that they have 4 heads. But what's happening with these is really independent of what happened over here. So this is a very weak argument, but I believe that it can be claimed that these are independent. So if they're independent, what would be the total probability here? What's the probability of this? Of getting this particular front end. This is a particular. It's not a binomial thing. If it's like you get heads, then tails, then heads. How likely is that to have that happen?
Is it P squared times 1 minus P?
Yes. Right. Now, allowing for this independence, which I'm struggling, but I'm probably just not seen this at this moment. But allowing for independence, what would this top thing be here? So it's just what it is. So 7 choose 4, p to the 4th times 1 minus p cubed. So this looks like a mess. Let me just try to wrap my brain around this. This is the event that we get. Well, actually, think about this. I mean, this happened, and this is just the event that we get in 7 tosses. We get 4 heads. What happened here has no bearing on whether this is happening or not. Okay. It doesn't have a bearing on it. It's just the total number of heads. See, that was decided here. There are 2 heads, so that means I've got 4 left. It's independent, you guys. But I guess that's the crux of the problem. But this is not what this student asked me. So what do we get as an answer here? You guys can do the calculation. What do we get as an answer? I need some space.
So yeah, well, so okay, yeah.
No, it's okay. Tell me what you got as an answer.
Well, yeah, the interesting thing is, okay, well, then once you do the multiplication, you're going to get p to the 6 times 1 minus p to the 4.
Yes.
Well, 7 choose 4.
Yes, okay, I got that, yeah.
And then times p to the 6, 1 minus p to the 4.
Yes.
All over 10 choose 6 times p to the 6, 1 minus p to the 4. So we can see that cancels out.
So the final answer is 7 choose 4, whatever that is. Over I don't know what this is. If you have a calculator, I mean, it'd be neat if it's something nice like 1 over 6.
Yeah, just give me a second. I'll do it.
Thank you.
Seven choose 4 is 35.
Yes.
And 10 choose 6 is 210.
Whatever that is. Is that 1/6? I think it's 1 over 6.
Yeah, 1/6.
Okay, now as Amos pointed out, this is weird. So what do you think the question was that this student who's now at Duke, is a PhD, which is a really good school for statistics, what was her question? She said, well, doesn't this depend on what P is? Because they said from the beginning it wasn't a fair coin. Why do they do that? That's called distraction. That's a distraction technique. When somebody gives you a question, they give you information that you don't need to solve the problem. I know this happens in the SAT and the GRE. It's very sneaky. They do this to students to see, well, you got to use this. They gave it to me because every problem I've done in my life, I got to use all the hypotheses. Apparently, you would have gotten the same answer here if you had P as a half, if it was a fair coin, because there ain't no P in the answer. And so she asked me this question. She says, Professor, can you tell me why there's no? Is there an easy way to do this? Because 1 over 6 sounds awfully simple. For maybe what might have been a complicated problem. And I have to admit, I'm sorry, you guys, I failed, her. It was like the first time I taught the course, and I said, I don't know. That's the answer is what you get is what you get. Life is like a box of chocolate. No, I didn't go there. No, but okay. So can somebody tell me why the P and the 1 minus P disappears from the answer? Why doesn't it matter?
I have to think about that. It feels like it should. Well, I think it's more that we already know that 6 heads occur. I know it has something to do with that because that's why the denominator is what it is.
Yeah. So what about the numerator?
In both situations, 6 heads occur.
Yeah.
Okay, 6 of them occurred. Now, what's the likelihood that just it happened to be HTH in the front? So, I feel like it's more the probability has less to do with how fair the coin is, and more to do with since we already have 6 heads and 4 tails. What's the likelihood that it happens to just be HTH at the front, given that it's really 6 heads and 4 tails? So the fact that the coin was flipped has something to do with it, or like how fair the coin was when it was flipped had nothing to do with it. That's what I'd say.
Yeah, I think that's as best as I can do. I mean, from a mathematical standpoint, I look at this, and you have situations where you, like Ames says, you've got 6 heads here. You got 6 heads here, so if when you look at the individual sequences, you have P to the 6, no matter how you cut it. You're going to have a P to the 6 and 1 minus P to the 4, and that's going to be in both. I mean, that part of it apparently cancels out, but that's part of the thing. Which, and I'm sorry, I probably did a worse job than Ames described it. I didn't do a better job. But this 1/6 bothers me also. It's like, if it's that simple, I mean, I'm looking at this and I'm saying, well, I've got three things. 3 factorial is 6. Is there something to do with that, or something like that? I can't for the life of me understand why the answer is so simple. And I just have to be honest. I don't know. I don't know why. And this was not the problem in the book. They had a different front end, and they had two different ones. But the two different ones that they had, this was interesting because they did not get 1/6. Ooh, gosh, darn it! It really depends. The final answer. And I hate to say this, I might have gotten this wrong, because the final answer in the book for their problem, I think they had. Let me check it. They had something to 450.
So I'm really sorry, but I've been kind of spacing out this whole class because I was thinking about work, which I was just doing, and I couldn't stop thinking about it. So, real quick, what is this problem supposed to find again?
It's a conditional probability, and maybe I made a mistake. If I made a mistake, I totally own it here, okay? Because the book, they have a different front end. They have a different front end, and they say for that front end, the answer is 1/10. So maybe maybe I need to start owning this mystery. But the question was, what is the probability that this is the front end you got, given that you had 6 heads occurred? And for them, let me just put down what they have.
So like the first few. So we're only, so HTH represents just the first 3 flips?
Yes.
Okay.
So they have this, head, tail, tail.
Given that 6 heads occur out of how many again? 10?
10.
Okay.
And you know what? They don't get the same answer I got. They get 1/10. But this is the same.
Yeah, but heads, tails, heads has 2 heads, and heads, tails, tails has 1 head. So
I know that, but this is very weird because I thought it doesn't depend on whether it's a head or a tail, because there's no P at the end of it, right?
Well, but it's going to change the number of ways that you would pick the the other part.
The remaining, okay, so you're saying F6, so
Yeah.
Like the coefficient is the part that would the combination right there. That's what would change, and that's why the number would change.
Okay, I'm dying. The curiosity killed the cat, so I'm going to be a dead cat here in a second. But what? Okay, so what is?
Intuitively, I also think like
let's see if we can do it, because you have how many heads occurring? 6, right? And what was this here? P to the 6 times 1 minus P to the 4th, right? And then what's the stuff up here? What's the story here? So you get this one. What's the probability of this? P.
That's P times 1 minus P squared.
And then I'm multiplying with this. So this is 6 heads and how many?
We have 5 heads left over.
P to the 5 minus P squared. Is that correct? I don't know. We have 5 heads, right? So I don't know what is this answer? Is this really 1/10? I hope it is, because then I can at least sleep tonight.
7 choose 5 is 21, and then over 210.
Oh wow.
What is that? Oh, I was worried that
Phew.
This is delicate. This is somewhat delicate. It even though in the final answer P doesn't matter, it somehow matters. Well, maybe P. It's not P. It's the number of. One of these is bigger than the other. This is smaller than 1/6. This is less. If 6, maybe this makes sense, because if you've got 6 heads, you would expect not to get only 1 in the first 3, right? I mean, that would be kind of that'd be less likely.
I was going to say, intuitively, I just think you're more likely to have heads in any one place. So
yes. Hold on, you guys.
You're
Let me check
likely to have 2 heads than 1.
Okay. Okay. Let me just let me give you a preview of what. The professor changed the problem. Yeah, I did change the problem, but I did the book problem down here.
So there's something that I think the entire, like for the last few lessons, I still haven't really understood. And that's why are we multiplying all these terms by like p to the 6th times 1 minus p to the 4th? Like,
okay, I can answer that quickly. Okay, let me answer that really quickly right now. Okay, that's a legitimate question. Let's just go back to coin flipping. Okay, let's just go back to coin flipping. Suppose you flip a coin 6 times, and X is the number of heads. Okay, let's take 6 tosses, and the probability of heads. Let's say that's P. Okay, so you have 6 tosses. 1, 2, 3, 4, 5, 6. Now you're going to get let's say what's the probability that X equals 3, say. Okay, so there's lots of ways this could go down. Okay, so you could get like heads here, heads here, heads here, something like that. There's lots of ways. But for any particular way, what is the probability of this? What's the probability of getting that particular sequence here? These are independent tosses, right? So these are independent. What happens here are independent. So you have to multiply the probabilities. And what do you get when you multiply the probabilities? P to the what? 3, 1 minus P cubed. Are you good with that? For this particular one?
Oh, that's the probability of getting that
exact sequence,
outcome.
right.
Okay.
But if you're looking for the probability that X equals 3, sorry, this is...
Yeah, that was... Okay, now it makes
I'm
sense.
sorry, you know what I mean? It's...
Okay.
You can see that whatever math I'm working on, it ain't this stuff. Okay, I'm working, but it's not this kind of thing. So the probability of X equals 3. Now, there's lots of ways that could happen, right? Lots of ways it could go down, that this could happen. Those 3 heads can be just about anywhere, right? I mean, spread out. They can be sprinkled in lots of ways. 6 choose 3 ways.
Yes.
So all of these are possible. They're disjoints. You can add them. And here you still have this. So this is different. This is a particular way. And how many particular ways could there be? Well, 6 choose 3.
Oh.
There's a lot of
and that gives us the
eventuality.
probability, so we're not even computing number of. So this isn't the number of possibilities; it's just the probability of it.
The probability. The number of possibilities is 6 choose 3, and they're all disjoint. These are all separate outcomes of your experiment. Your experiment would be a sequence of tails and heads. Okay, your sample space, and there's a lot of sequences that have 3 heads and 3 tails.
Mm-hmm. Cool. So we're just. So I was used to. I guess why I was confused is I just got so used to writing these probability problems as, number of possible, or no, number of outcomes that you're looking for divided by the sample space, and rather than
they're not equally. Only if P is a half. You see, they're not all equally likely. The head. Okay, how to think? I guess they are if you specify the number of heads and the number of tails, right? So it is if you make that specification. So that's why this is equally likely for that case. But if you switch around the number of heads, it changes. You see, if it had been a fair coin, 1 head and 5 tails would be the same as getting 5 heads and 1 tail, something like that.
Okay.
All right, you guys. Okay,
so
so
that's where this whole multiplying by the probability just comes in handy, right? So like.
That's okay. This is a true statement about all of mathematics. That independence is critical to make calculations. You cannot do hard stuff without independence. You can't. And my dad told me that a lot of papers in probability are flawed, that they did not prove that the events in question were independent. And so that's why I'm worried about what I wrote over there, right? I'm worried about that the answer in the back of the book could be wrong, okay, or not. It's not correct to make that. Okay, so let me see what time I have. I've got a couple of minutes here. Let me give you a problem from the next section, which is kind of just to tell you the power of the techniques in the next section. We're looking for some expected expectation of something, okay? And now you have a stick of unit length, and you have a point that in advance it's a point between 0 and 1, and in advance that's been laid down, okay? So somewhere between 0 and 1 is a point that's been selected, okay? Say it's here.
Oh, right. This is where it starts to get continuous, right?
Yep.
Cool.
Okay, and forgive me for the cheesy jokes that I'm always telling. It's like you know when it's coming. But anyhow, you have a stick and you have a point. Now, we want the expected length. You're gonna break the stick at random at any point. So you're gonna break the stick at U, and U is uniform 0, 1. And to show that it actually broke someplace, well, whatever, just uniform 0, 1. So maybe I'll use a different color here, the notorious purple thing. So the stick will break random. You're going to break randomly anywhere along here, okay? So the E is the expected length of the portion of there's two, it breaks into two, of the piece of the stick that contains P. So we want to know what's the expected length of the piece that contains point P. So, okay, so let's see. Suppose
So
that
is P arbitrary or
no,
random?
P was set from the beginning. It was set from the beginning. Okay? So suppose we break here, okay? This is the break. What is the length of the piece of the stick that contains P?
It's whatever the length of the right side is, which is
Well, just this, right? Right?
Mm-hmm.
It would be 1 minus wherever you broke it. U, if U is where you broke it.
Ah.
So I'm sorry, guys. If this is a gambling game, what do you not want to have happen?
have it be on the other side.
You don't want the short end of the stick. But okay, suppose it was a gambling thing, okay? And you want to maximize the expected length, okay? Okay, this is it, man. This is it. We're in home stretch, you guys. This is it. This is it. This is the question. If we have one break.
I thought this was going to be a simple problem.
It is a simple problem if you picture it. So where do you think I should? Okay, what if the break was right here? Then this would be the length of the piece, right? So let me ask you this question. This is what you go home with. I know you're at home, but you go to your bedroom with it. What is the expected length of the piece that contains P? And where should we position P so that we do the best? That our expected length in containing P is along this. Just intuition. You see, if the P is getting towards an edge, you have the potential to get a really long part. See, you understand that? If you break here, then you have this really long piece that contains P. Do you guys understand the question?
Yeah.
Short end of the stick.
It's taking. I've been thinking really hard for a minute now. I feel like it's 1/4 or 3/4 of the way through. So
okay. So let's do that. Okay, let me do that.
Put it at 0.75.
This is half. So you want to put P? You would say right here, right? Is that a quarter? Maybe it's not quite. Oh, come on, Di. I can do better. Let's try it again, okay? Yes, how about that?
Yeah.
So there's P. So now if I break it here, I get a pretty good thing, right? But if I break it here, how much do I get?
Still really big.
Basically, I'm avoiding the short end of the stick, which we all know you want to do, right? Okay, but suppose you know the answer, or your intuition, aim is cogitating, I can see. So you know the answer, but then it comes to the question of how do you prove it? And this, you guys, is the power of calculus, because things that are intuitive may not be true all the time, but when you have calculus in algebra and things like that, then you can establish it, and you'd be surprised now and then what you think is obviously true is not, okay, because we couldn't have conceived of a counterexample. So let me ask you guys that are here with me. How many do I have? We've lost a few. Where should I put P so that when I snap this at it randomly, in other words, I could snap it anywhere with equal likelihood. Where do I put that point P so that the length of the substick, the length of the piece of stick that contains P is longest, or we expect it to be long, you know what I mean? Where so that on the average it will be longest. And I think Ethan's come up with an idea. I think what he's saying is, and I don't think I did this justice, but anyway, what he's saying is, how about a quarter from the wall? When I first looked at this problem, I have a bad habit of looking at problems in a book and not reading what they say about them. I said, put the P at the end, because, you know what I mean? I got a chance I can really get a big number there,
Yeah, I was thinking that too.
If I put it at the end, like, listen, way over here, then look, I mean, if he's anywhere over here, I'm doing really good. If he breaks it here, I get a huge thing. So on the average, I would expect, got some huge stuff in there. The mean will follow the outliers, okay? Because when we talk expectation, you're talking mean, okay? It's going to follow the outliers. So my supposed knowledge of statistics told me to put it at the end, not at the quarter point.
I also thought maybe the half, or maybe even 2/3 or 1/3.
Have you ever seen anything like this?
In 341, I know that there was like just like the question was, what is the expected length of the longer side? So same scenario. There was no point though. Just you have a string of length 1, and it's going to get cut somewhere randomly. Mm-hmm. What is the expected length of the longest side?
I think that's equivalent to P right in the middle at 0.5.
No, I don't think it was 1/2, because
no, it's equivalent to putting P at 0.5, I think.
Okay, maybe, I don't know. Point is, I don't even remember exactly how to do that one anyway. So
maybe we could figure it out. So you're saying here's a string, right? And you're saying if I cut this randomly,
you just cut it randomly. What's the length of the longer side of the string?
I believe that's Ethan. I think it's a different question. I think it might be different.
It is a different question, but I think the answer of the expected value of the longer side is equivalent to the expected value of this problem if P were put in the exact center, because then P tracks the longer side.
Well, you guys, could we calculate it? I'm sorry, I'm probably over.
Yeah, you're right.
We're already over time.
I'm sorry, but I mean, you could calculate this one by expectation, right? Because it'd be 0 to 1.
Yeah, that's what I was thinking to do.
One is the density function, and then
whichever side it goes on, it's
so x. Wait. So the length of the longest side, it depends. Let's go to. Oh shoot.
Yeah, exactly. Like, hold on a minute. I got to think about this. I did it before. I can't remember how I did it.
Symmetry.
I mean, we could come back to it next week.
Yeah.
We better
let people go here.
Yeah, that problem where it's just the longer side, that's way easier because we can just exploit the symmetry. I'm thinking from the physics perspective again. It's equally likely to be on the left as the right, and on the left and the right, it's equally likely to be in anywhere in a range from 0 to 0.5, basically.
Yeah. You basically calculate an expectation. You have to calculate an expectation.
Yeah. So the expectation is basically the expectation value of random from 0 to 0.5 plus 0.5.
Well, but there's two cases. Yeah, okay.
So then the expected value would be 0.75, I think.
Yeah, no, what you said, Professor, I think is the key to doing that problem is, okay, well, if you cut it in the first half, the length would be based on, from the cutting point up to 1. If you cut it in the second half, it's from 0 to the other one. So you just kind of split it up. You've got 2 cases, and then you're good to go.
I think so. I think this one is a little more complicated. I'm not sure, but
Yeah, I think what I have is an easier problem. The way you have is a bit more complicated.
but you know what? You guys have been awfully polite, and we're bleeding people right now. I feel like I pontificate too much as it is. But you guys could help me by reading this introduction to chapter 5, where they do some sort of simplicity things. Not this, but the first thing they hit that's not simple, that I couldn't conceive of by myself without help from calculus, was this problem. This is the very first problem, and so that's a goal. Something interesting, because the other stuff is just sort of, he's checking if you remember how to integrate polynomials and stuff, and it's very boring. But this is not boring, so.
Okay, but we could read up on chapter 5.
Just start.
Just start going through the first few examples. Sure thing.
All right, you guys. Okay, look, I really need to let you go. You've been awfully polite, and I know it was a little bit disjointed today, but that's just life. So, okay, you guys. Unless there's a question, I'll let you go and shut it down.
Thank you.
All right.
Later.
Take care, Professor.